Hi, and welcome to this week's video lesson in astronomy, patterns in the night sky, where we're going to learn about the location and movement of stars. It's super cool, so let's get right to it. Here are our goals for this week. Our learning goals are: I can describe the location and movement of individual stars and groups of stars or constellations as they move through the night sky. I recognize that the apparent movements of objects in the night sky is regular and predictable. I can explain how this apparent movement is related to Earth's rotation. And our language goals: I can talk about stars using words like rotation, constellation, asterism, and apparent movement. Do the stars move? Well, if you were to turn on a video camera and leave it out all night, you would notice that the stars do seem to drift across our sky in a motion from east to west. The stars aren't really moving, though. They just look like they are. In fact, we're the ones that are moving. We're riding on the Earth at a speed of about 1,700 kilometers per hour as it spins on its axis. This spinning is called rotation. It's a really important concept for you to understand. I'm going to talk about it in a little more detail next, but I just wanted to highlight that word, a very important vocabulary word and concept: rotation. All right, are you dizzy yet? Now that you know that you're spinning on the Earth at a speed of 1,700 kilometers per hour, that is fast. Okay, well, let's talk about rotation a bit. So this image shows the rotation of the Earth on its axis. The axis is an imaginary line from the North Pole to the South Pole. It spins around that. The Earth completes one full rotation every 24 hours, and that's what gives us our night and day. During the time that our part of the Earth is facing away from the sun, it's night. And the other half of the time, we're pointed towards the sun, so it's light, daytime. That's rotation of the Earth on its axis. And that's what causes the stars to appear to move across the sky. So see this picture and imagine it's that Earth is just sitting surrounded by stars on all sides, because that's the reality. Now, you are moving. They are standing still. But it looks to you, because you think you're standing still, that those stars are actually moving, when in fact, you're the one who's moving. It's kind of like if you're in a car and you're stopped at a stoplight and there's another car beside you, or maybe a bus. Sometimes it's more noticeable if it's a bigger vehicle. And that vehicle starts to move and you feel like you're actually moving. You feel like you're going backwards. But you look and you realize, no, our car is staying still, but the bus beside me is moving forwards. So it's that same kind of thing. It's based on your perspective. We feel like we're staying still, and so we think that those stars are moving, but actually we're the ones who are moving. So that's what we call the apparent movement of the stars. We say apparent because it appears that they're moving, when in fact, they're not the ones that are moving. All right, so that's one kind of movement that we see, is that daily drift or nightly drift from east to west across the sky as the Earth rotates on its axis once every 24 hours. The other kind of movement that we see, the other pattern of movement we see, is called seasonal movement. So not only do the stars seem to move across the sky from east to west every night, as I talked about just a moment ago, they also seem to shift around the sky with the seasons. So let's learn a little more about that. In order to do so, we have to understand about a very special star that we have in the northern hemisphere. Now, in the northern hemisphere, the stars in the night sky seem to rotate around a central point, a star called Polaris. Polaris is also known as the North Star, and the reason for that is that it's located pretty much directly above the North Pole. This picture shows what are called star trails, and they show how the stars seem to move with the seasons around the North Star, which you can see here. This little dot, Polaris, it doesn't have a trail like these other stars have a trail. So this image was taken over a period of days and weeks to show that movement of spinning around Polaris. It's a different kind of movement from that daily east to west drift that we looked at originally. This is called seasonal movement. Let's learn a little bit more about Polaris because I want you guys to be able to see Polaris. It's actually really special. The southern hemisphere doesn't have a pole star, okay? So we do in the northern hemisphere, and it's very helpful because if you can find Polaris, you always know which direction north is. And that was really, really helpful for people before the invention of the compass and other navigational tools in order to be able to know what direction they had to go in as they were traveling. So Polaris is a hugely important star. And because we can see it in the northern hemisphere, that's going to be one of your assignments, to find Polaris in the night sky. So to be able to find Polaris, you need to be able to find the Big Dipper. But I'm hoping, because it is kind of the most famous and easy to find constellation in the northern hemisphere, that you've all seen it, you can all recognize it, you can all pretty easily find it. If not, we are also going to be making some planispheres or star finders that'll help you locate the Big Dipper. But I also bet if you have an older sibling or learning coach that they could easily point out the Big Dipper for you in the night sky on a day when it's not cloudy, obviously. So this diagram shows us how to find Polaris by simply drawing an imaginary line straight through the two outermost stars of the Big Dipper to the next brightest star, as you can see in that little animation. So what's the bowl of the Big Dipper, you ask? Well, it's this part right here, because the Big Dipper is called a Big Dipper because it's like a dipper or like a soup ladle or a big spoon, a serving spoon, right? And so the bowl is the part that you scoop the soup out with, let's say. And the outermost stars of that are here on the farthest outside, farthest away from the handle, and they point right towards Polaris, which conveniently is attached to the Little Dipper. Now you might notice that Big Dipper and Little Dipper are in brackets on this diagram, and that's because they're not the official names of those two constellations. They're just the names, the popular names that people who speak English typically call them. But to many people, in fact, most of the constellations that we sort of see as being the accepted constellations come from ancient Greek mythology. We'll learn a bit about that. Many other people had different names for different constellations. They saw different patterns, or even if they saw the same patterns, they had different stories about them. We're going to learn a lot about what the Indigenous people of Canada named the constellations and how they viewed the constellations and used the same stars as the ancient Greeks did. But for now, we're going to talk about the ancient Greek terms for them. And actually, these ones are Latin because we've talked about this confusing use of Greek and Latin in English. And yeah, here's another example of it. It's not just tetrominoes and quadrilaterals, it's also in astronomy. So Ursa Major means Great Bear or Big Bear. And this is only part of the Ursa Major constellation. We'll look at the rest of it another time to see how it does make the shape of a bear. And then Ursa Minor is the little bear. So it's like a mama bear and a baby bear. But if you think of it as a spoon, it's really easy to be able to find the location of Polaris, the North Star. So keep all of that in mind as we go along. All right, so let's talk about the seasonal movement of Ursa Major as it moves around Polaris, the night star. They're all night stars, Miss Clark. Oh my gosh, the North Star. This diagram shows how we see the Big Dipper at this time of year in winter. So this might help you find it. If you go outside and you're looking for it and you're like, nothing looks like a spoon. Well, look for a spoon that's standing up on its end, kind of like this, as if it were standing on its handle. So in winter, this is how we see the Big Dipper in our night sky. Take a moment and predict where you think the Big Dipper might be in the other seasons, in spring, in summer, and in fall. So here are the positions of Ursa Major or the Big Dipper in our night sky, if you're looking up at the sky, in relation to Polaris, the North Star, at different seasons. So in winter, it looks like it's standing on the tip of its handle. In fall, it looks like a nice spoon that you're ready to drink your soup out of. In summer, it kind of looks like you're serving that soup. And in spring, it's upside down, spilling the soup everywhere. But what I want you to really notice is how the bowl of the Big Dipper, the bowl part, remember, the scoopy part, is always pointed towards Polaris. And I'm wondering if anybody has made any connections yet to what we just learned about in transformations in math when you see this diagram of the seasonal movement of Ursa Major around Polaris. Take a moment and think about that. Could you describe the movement of the Big Dipper around Polaris using one of the geometrical transformations that we learned about? Did you say that this is a rotation? If you did, you're right. The Big Dipper rotates about Polaris as its point of rotation, and it rotates in a counterclockwise direction. Such a cool connection between math and science right here. All right, take a second to stop and think. If the stars and constellations appear to move across the sky from east to west every night because the Earth is spinning on its axis, rotation, what do you think might be the reason why the constellations also seem to move from east to west with the seasons over a period of a year? And that's that counterclockwise rotation we talked about is the same as moving from east to west, but it takes a whole year to complete that instead of a single day. Think about that for a minute. All right, big explanation coming up. As you know, the sun is at the center of the solar system, and the Earth is moving around the sun. While it's doing this, it's also rotating on its axis. So our Earth rotates on its axis, it spins on its axis once every 24 hours. So you can see this Earth here, imagine, and you see the axis, which is this line going from the North Pole to the South Pole. We'll talk about why it's tilted later. But it's spinning. Every day it spins. But while it's spinning, it's also moving in this big path, which we call an orbit, around the sun. And we move in a counterclockwise direction, as you can tell from these arrows. So we know that it's not really the stars that are moving, but it's actually the Earth that's moving. And this movement, when we travel in our orbit around the sun, is called revolution. And it's the revolution of the Earth around the sun that appears to make the constellations move in that counterclockwise rotation around Polaris over the seasons. This revolution, as I said before, is also called the Earth's orbit. Now remember, we were spinning on our axis at 1,700 kilometers per hour. We are orbiting the sun at over 100,000 kilometers per hour. So we are spinning around in circles and moving around the sun at incredible speeds. So it kind of really boggles the mind when you think about it, but it's this movement that makes the stars appear to move in the sky, even though they're not really moving compared to us. It's us that's doing the moving. It just seems like it's the stars. So we have that daily drift from east to west across the sky that's caused by our rotation on our axis, spinning around, and that rotation of the constellations, that way that the constellations appear to be moving around the pole star Polaris, is caused by the Earth's annual revolution or orbit around the sun. And when I say annual, I mean once a year. So it takes a day for our Earth to spin one full rotation on its axis. It takes a year for the Earth to revolve around the sun or travel in its orbit. So rotation once every 24 hours, revolution once every 365-ish days. So I kept saying the stars aren't moving, we're the ones who are moving. And that's mostly true. From our perspective, the stars do seem to be perfectly stable and unmoving once we understand our own movement, that is. But actually, I was lying. Stars do move. It's just bear with me. All of the stars in the universe are actually moving. They're all expanding away from each other, running away from each other at massive speeds. So I'm going to explain briefly. We don't have to focus too much on it, but our solar system orbits the center of our galaxy, which is called the Milky Way. And we do that at over 200 kilometers per second. That's even faster than the speed at which we are orbiting the sun. So, guys, we are racing through space, just racing through space all the time. And the galaxy is hurtling through space at approximately 19 kilometers per second. So, this galaxy of ours, the Milky Way, spinning, 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 also moving through space. So, it's like everything in space is spinning and also moving away. So, along with the Milky Way, every other galaxy is also racing away at around the same breakneck speed. And that's because the entire universe is expanding. Everything in the universe is rushing quickly away from the point in both space and time at which the Big Bang occurred, which was the creation of our universe. And that actually is something that the James Webb Space Telescope that we've talked about is studying. So more on that later. But this motion of the whole universe expanding and the way the constellations appear to us as a result of that motion does cause some movement, but we can't see it because it only moves very slowly over thousands of years. But let's talk about it. In our lifetime, the stars appear completely stable, but in the grand scheme of the history of the billions of years that the universe has existed, yes, they move. Here is a GIF that shows how the Big Dipper, again, that's perhaps the most recognizable constellation in the sky for the northern hemisphere, has changed over the past 100,000 years. And you can see the dates here. So it's going BC and is going to come up and catches up with us and goes way past us pretty quickly. It's going very, very fast because this is from 100,000 years in the past to the present and then the next 100,000 years. So this is happening because of the way all of those galaxies and stars are flying away from each other. So what do you need to know from this lesson? Mostly the stars are pretty stationary. They do move, but it's not really perceptible to us in our tiny lifetimes compared to how long the stars have existed. The daily movement of stars that seem to drift across our sky from east to west is caused by the Earth's rotation, which happens once every 24 hours. That's what gives us day and night. The movement of the constellations through the sky in a counterclockwise rotation around the North Star, Polaris, is caused by the Earth's revolution or orbit around the sun, also in a counterclockwise direction, which happens once every year. I hope you enjoyed this lesson. We'll talk lots more about this and more. I hope you enjoyed this lesson. It's a lot to take in, but it's so, so cool. We'll be talking lots more about this and coming to terms with the way, with the patterns that we see in the night sky and the way the stars move as we continue this unit.